Jupiter, a colossal giant in the vastness of space, commands attention with its stormy atmosphere, massive moons, and gravitational dominance. As the largest planet in our solar system, it not only shapes the structure of our cosmic neighborhood, but also as a protector, guarding inner planets from potential threats. Long before Galileo Galilei made his monumental discovery, the world held a vastly different view of the universe. For centuries, humanity believed in a geocentric model, the idea that the Earth sat at the center of the universe, with all celestial bodies revolving around it. This belief was so deeply ingrained that it became a cornerstone of Western thought. However, in the early 1600s, a new era in science was beginning to take shape, and it was Galileo who would play a pivotal role in challenging this worldview. Galileo, born in 1564 in Pisa, Italy, grew up during a great time of intellectual and scientific transformation. His early education was in medicine, but his interest soon shifted to mathematics and physics. By the time he was in his 30s, Galileo had already made significant contributions to the study of motion and mechanics. His work on the law of falling bodies and the development of the improved telescope laid the foundation for his future discoveries. In 1609, Galileo turned his attention to the night sky, using his modified telescope to study the stars and planets. His observations led him to one of the most profound discoveries in the history of science. On January 7, 1610, after months of intense observations, Galileo noticed that Jupiter appeared to be accompanied by several tiny star-like points of light, each orbiting the planet in a regular pattern. These were the moons of Jupiter: Io, Europa, Ganymede, and Callisto. Galileo's discovery was revolutionary for several reasons. It not only provided clear evidence that there were celestial objects orbiting another planet, but it also undermined the long-standing belief in an Earth-centered universe. If moons could orbit Jupiter, why couldn't other celestial bodies orbit the Sun? Galileo's findings directly challenged the geocentric model and provided strong support for the heliocentric theory proposed by Copernicus, which stated that the Earth and other planets orbit the Sun. In his landmark work, Sidereus Nuncius' Starry Messenger, published in 1610, Galileo documented his observations and presented evidence of Jupiter's moons to the scientific community. The book became an instant sensation and sparked widespread debates. For many, it was the first concrete proof that the universe was far more complex than previously imagined. Galileo's discovery marked a turning point in the history of science, but it was not without controversy. The Catholic Church, which supported the geocentric model, initially condemned the heliocentric theory as heretical. Galileo's outspoken support for Copernicus's idea eventually led to his trial and house arrest in 1633. However, despite this, his work continued to influence generations of scientists and changed the course of astronomy forever. Jupiter's moons, which Galileo had once observed as tiny points of light, continue to be a source of fascination for astronomers today. They have been studied in great detail by spacecraft such as NASA's Galileo and Juno missions, and their importance extends beyond their historical significance. These moons, with their unique characteristics and potential for harboring life, remains key to our understanding of planetary systems, both in our own solar system and beyond. Jupiter, the giant of our solar system, reigns supreme as the largest planet orbiting the Sun. Known for its swirling storms and captivating beauty, it has been a subject of human fascination since antiquity. This gas giant, fifth from the Sun, is not only a cornerstone of classical astronomy, but also a key to understanding the processes that govern planetary science and celestial mechanics. Our exploration of Jupiter reveals not just the secrets of one planet, but also gives insights into the formation and evolution of our solar system, potentially extending to exoplanetary systems throughout the Milky Way. In ancient Mesopotamia, Jupiter was revered as Marduk, the head of the Babylonian pantheon. This association was not only religious, but also astronomical. The Babylonians were among the earliest to systematically observe the heavens, maintaining detailed records of celestial movements. These observations were integral to their development of a lunar calendar and contributing to their understanding of planetary motions. Jupiter, with its steady and bright path across the sky, was associated with rulership and authority, mirroring Marduk's divine status. Their keen astronomical insights manifested in the creation of the Enuma, Anu, Enlil, a comprehensive series of cuneiform tablets that detailed celestial omens and linked planetary positions to terrestrial events. Jupiter's appearance and movements were closely studied to predict significant occurrences, shaping both divinational practices and administrative decisions within the empire. The Greeks identified Jupiter with Zeus, the supreme god of the Olympian pantheon. Zeus was the embodiment of sky and thunder, ruling over gods and humans alike. This connection emphasized Jupiter's magnificence and power, aligning the planet with divine rule and cosmic order. The Greeks were instrumental in laying the groundwork for Western astronomy. Philosophers like Pythagoras and Ptolemy utilized geometry and mathematics to decipher the heavens. Ptolemy's geocentric model, which placed Earth at the center of the universe, held sway for centuries. Although later disproven, it demonstrated the importance of celestial bodies in guiding philosophical and scientific thought. Greek skepticism and inquiry prompted thinkers like Aristotle to consider the nature of planetary motion and the structure of the cosmos, where Jupiter's role was crucial given its prominence. This inquiry into the natural world laid the intellectual foundation for future astronomical advancements. For the Romans, Jupiter was more than just a planet. It was the divine protector of the Roman state, symbolizing authority, law, and moral judgment. Jupiter Optimus Maximus, as he was known, was worshipped in grand temples, most notably the Temple of Jupiter on Capitoline Hill. This temple served as the religious center and symbol of Rome's enduring power. Astrologically, the Romans assigned significant meaning to Jupiter's movements, influencing personal and political decisions. The alignment of planets, including Jupiter, was consulted before major events, such as wars or governmental changes. Jupiter's perceived benevolence and influence were thought to bring prosperity and success, amplifying its cultural significance. Jupiter's formation began over 4.5 billion years ago, during the early stages of the solar system's development. As the solar nebula, the vast cloud of gas and dust, collapsed, the Sun formed at the center, and the remaining material began to coalesce into planets. Jupiter, being one of the first planets to form, rapidly accumulated gas and dust left over from the Sun's formation. This process, known as accretion, allowed Jupiter to gather massive amounts of material, enabling it to become the gas giant that we know today. It is believed that Jupiter's early growth may have played a key role in shaping the solar system, notably by influencing the orbits of other planets and potentially helping to prevent the formation of a second star. The core of Jupiter remains one of the greatest mysteries in planetary science. It is believed to be composed of a mixture of rock, metal, and icy materials, although there is still significant debate among scientists regarding its exact composition. Some theories suggest that Jupiter's core is made out of dense ice, while others propose a combination of rocky and metallic substances. This uncertainty stems from the challenges of studying the planet's interior, which is obscured by its thick and turbulent atmosphere. The core is surrounded by a vast, dense layer of hydrogen and helium gas, which accounts for most of the planet's mass. As pressure increases with depth, hydrogen is transformed into a metallic state. This form of hydrogen is highly conductive and contributes to the planet's magnetic field, which is one of the most powerful in the solar system. Jupiter's internal structure is difficult to study directly due to its thick clouds, but scientists have gathered valuable data through indirect methods. The Juno spacecraft, currently in orbit around Jupiter, has been instrumental in providing insights into the planet's mass distribution and internal composition. By studying Jupiter's gravitational and magnetic fields, Juno has helped reveal details about the planet's deep structure, including the likely extent of its core and the nature of its atmospheric dynamics. These measurements continue to improve our understanding of how Jupiter formed and evolved, offering clues about the processes that shaped not just this gas giant, but other planetary systems across the universe. Jupiter's formation and migration are key to understanding the configuration of our solar system. While it is believed that Jupiter began in a closer orbit around the Sun, theories such as the Grand Track hypothesis suggest that the planet migrated outward, moving past Mars's current orbit before settling in its current position. This migration is thought to have played a major role in shaping the solar system's architecture. As Jupiter moved outward, it scattered smaller bodies and helped to clear the space around it, potentially influencing the formation of the asteroid belt. This migration process also had a profound impact on the distribution of materials in the early solar system, most notably the icy bodies that now reside in the Kuiper belt and the Oort cloud. Jupiter's gravitational influence may have contributed to the clearing of the region, as it either ejected or prevented the consolidation of potential planets in the outer solar system. Some hypotheses even suggest that Jupiter's migration helped stabilize the orbits of other planets, including Saturn, and may have helped prevent a chaotic configuration where multiple gas giants could have destabilized the inner solar system. Furthermore, Jupiter's migration likely played a pivotal role in shaping the orbits of smaller bodies, including asteroids, comets, and moons. By interacting with these objects gravitationally, Jupiter acted as both a regulator and a protector, influencing the trajectories of many bodies in the solar system, and potentially preventing frequent collisions with the inner planets, including Earth. Jupiter's powerful gravitational field and early migration helped establish its role as a planetary guardian, shielding the inner planets from potential impacts and contributing to the stability of the solar system. Jupiter's atmosphere is a stunning example of atmospheric dynamics, where a complex mix of gases creates a variety of fascinating phenomena. Primarily composed of hydrogen and helium, with trace amounts of methane, ammonia, hydrogen sulfide, and water vapor, this atmosphere gives the planet its iconic banded appearance. These bands consist of zones and belts, which result from Jupiter's differential rotation and powerful east-west winds, some of which reach up to 640 km per hour. One of the most recognizable features of Jupiter's atmosphere is the Great Red Spot, a massive anticyclonic storm that has been raging for at least 350 years. While recent observations from the Hubble Space Telescope show that the storm is slowly shrinking, it remains a dominant feature of the southern hemisphere. Scientists study the Great Red Spot to understand the dynamics behind long-lived atmospheric phenomena, not only on Jupiter, but also on Earth and beyond. In addition to the Great Red Spot, Jupiter is home to countless smaller storms, vortices, and other atmospheric disturbances. These features offer a natural laboratory to scientists studying fluid dynamics and meteorological processes. The planet's atmosphere is also known for intense lightning storms, auroras, and seasonal changes, all driven by Jupiter's rapid rotation and the immense heat generated within. Jupiter's auroras are particularly striking and vastly different from Earth's, thanks to its powerful magnetic field, one of the strongest in the solar system. Jupiter's auroras are much larger and more energetic. They are created by interactions between charged particles from Jupiter's magnetosphere and solar winds. In fact, Jupiter's magnetic field is approximately 20,000 times stronger than Earth's, generating a vast magnetosphere that extends nearly 3 million kilometers towards the Sun, and as far as Saturn's orbit in the opposite direction. This enormous magnetic field is produced by the movement of metallic hydrogen within Jupiter's core, combined with the planet's rapid rotation. The magnetosphere traps charged particles, forming intense radiation belts that present significant challenges for spacecraft exploring the Jovian system. Understanding Jupiter's magnetosphere is crucial not only for studying planetary magnetism, but also for gaining insights into the processes that govern magnetic fields across the universe. Within Jupiter's magnetosphere, plasma toruses and intense radiation zones are especially prominent around the Galilean moons. These dynamic structures are influenced by volcanic activity on Io, which ejects material into space, contributing to an ever-changing and energetic environment. The observation of Jupiter's moons by Galileo Galilei in 1610 revolutionized our understanding of the cosmos. Through his telescope, he identified 4 objects near Jupiter, initially believed to be stars, but later confirmed as moons orbiting the planet. Galileo's groundbreaking publication, Sidereus Nuncius, unveiled these findings, challenging long-held views of celestial motion. Today, Jupiter's 79 known moons form a dynamic system, each with unique features, from volcanic activity to icy surfaces, offering vital clues to the complexity of planetary formation and the potential for extraterrestrial life. Io, the closest moon to Jupiter, is the most volcanically active body in the solar system. Its surface, marked by lava flows, volcanic pits, and sulfur plains, undergoes constant renewal due to tidal heating. The intense gravitational pull from Jupiter, combined with the tug-of-war from the neighboring moons Europa and Ganymede, causes Io to stretch and compress, creating friction that heats its interior and powers the constant volcanic activity. The most dramatic volcanoes on Io, such as Philae and Loki, erupt plumes of sulfur and molten rock, which can rise hundreds of kilometers into space. The volcanic activity on Io not only makes it an intriguing target for planetary scientists, but it also plays a role in the broader Jovian system. Volcanic material from Io contributes to Jupiter's magnetosphere, and the particles ejected by these eruptions can form a thin ring of dust around the planet. Io's extreme geological activity has made it an essential study in understanding tidal heating mechanisms, not only in our own solar system, but in exoplanetary systems as well. Europa, the smallest of Jupiter's Galilean moons, has garnered significant attention due to its potential subsurface ocean. Beneath its icy crust, scientists suspect there is a liquid water ocean, possibly warmed by tidal heating from the gravitational interaction with Jupiter and other moons. This ocean could harbor the necessary conditions for life, making Europa one of the most promising places to search for extraterrestrial life. Europa's surface is covered in a thin layer of ice, marked by cracks and ridges that suggest active cryogeological activity. Some researchers believe that these features may be the result of a subsurface ocean that shifts, pushing ice sheets around. The Moon also displays signs of past cryovolcanic activity, with bright ridges and smooth plains, further hinting at an active interior. Future missions, such as NASA's Europa Clipper, will closely examine these surface features and help determine whether Europa's oceans could indeed support microbial life. Ganymede, the largest moon in the solar system, is unique not only because of its size, but also because it possesses its own intrinsic magnetic field, likely generated by a partially liquid metallic core. This magnetic field is a key feature, as no other moon in the solar system has been observed to have one. It adds a layer of complexity to our understanding of planetary magnetic fields and provides valuable information about the interior structure of moons. Ganymede's surface is a mix of older, heavily cratered regions and younger, tectonically active areas. The Moon is thought to have subsurface oceans, which may be sandwiched between layers of ice and rock. This ocean could be in contact with a rocky mantle, possibly offering the chemical conditions needed for life. Ganymede also experiences auroras at its poles, which are driven by its magnetic field interacting with Jupiter's powerful magnetosphere. It is a mix of features, and its potential for subsurface oceans, Ganymede holds a wealth of scientific possibilities. Studies of its interior could reveal more about the processes that shape not only moons, but also planetary bodies in general. Callisto, the outermost of the Galilean moons, presents a stark contrast to its volcanic and icy siblings. The surface of Callisto is heavily cratered, with no signs of recent geological activity. This ancient surface provides scientists with a record of early solar system bombardment, and studying it offers a glimpse into the early history of the solar system. Unlike Io and Europa, Callisto shows little evidence of internal heating or active geology, which makes it one of the most preserved moons in the solar system. Despite its lack of geological activity, Callisto likely harbors a subsurface ocean. This ocean is thought to be located beneath a thick layer of ice, similar to Europa's. However, unlike Europa, Callisto's lack of geological activity suggests that its ocean is much less likely to be in contact with the Moon's rocky mantle, reducing the possibility of the ocean harboring life. Still, Callisto remains an intriguing target for further study, especially in understanding the formation and evolution of icy moons. The scientific exploration of Jupiter began with the advent of ground-based telescopes and advanced into the realm of space exploration, marking an exciting journey of discovery. Over the decades, dedicated missions and technological advancements have provided us with an ever-deepening understanding of the gas giant and its moons. The first close encounter with Jupiter were achieved by the Pioneer 10 and 11 spacecrafts in the 1970s. These missions provided the first detailed images and data revealing Jupiter's intense radiation belts and magnetic environment. Following closely, Voyager 1 and 2 captured high-resolution images of Jupiter's atmosphere, rings and moons, significantly expanding our knowledge of the Jovian system. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, revolutionized our understanding of the planet and its moons. Galileo made the first direct observation of a comet impacting a planet when comet Shoemaker-Levy 9 collided with Jupiter, highlighting the planet's role as a cosmic vacuum cleaner. Launched in 2011 and arriving at Jupiter in 2016, The Juno spacecrafts aim to unlock the planet's secrets, including its composition, gravity field, magnetic field, and polar magnetosphere. Juno's data continue to shed light on Jupiter's structure beneath its dense clouds and its potential solid core. In the future, NASA's Europa Clipper and ESA's JUICE missions will help explore Jupiter's icy moons, mainly Europa and Ganymede. They will study whether these moons could support life, map their frozen surfaces, and look for signs of life, past or present. These missions will not only teach us more about Jupiter, but also help us learn how planetary systems form and change over time. This research also brings us closer to understanding if life could exist elsewhere in the universe. By capturing or deflecting comets and asteroids, Jupiter reduces the likelihood of collisions with Earth and other terrestrial planets. This protective mechanism extends back billions of years, shaping the conditions that allowed life to evolve on Earth. Jupiter's gravitational dominance not only acts as a shield, but also as a cosmic slingshot, occasionally redirecting objects inwards towards the Sun. These interactions have paradoxically brought both destruction and essential building blocks for life, such as water and organic molecules during the early solar system's formation. This duality highlights Jupiter's profound influence on planetary habitability, underscoring its pivotal role in the delicate balance of the solar system. Jupiter's role in celestial mechanics provides valuable insights, not only for understanding our own solar system, but also for the study of planetary systems around other stars. The discovery of exoplanets has revealed that gas giants like Jupiter are common in other systems. These planets, known as hot Jupiters and cold Jupiters, depending on their distance from their parent star, offer a unique opportunity to study planetary atmospheres, migration, and evolution. Jupiter's impact on the formation and arrangement of planets in its system provides a useful framework for understanding how similar planets might influence the dynamics of distant planetary systems. Moreover, by comparing Jupiter's influence with that of exoplanetary gas giants, scientists gained a deeper understanding of atmospheric behaviors, magnetospheric interactions, and the potential for moon systems. This comparative approach offers a broader view of how gas giants contribute to the development of planetary systems, enriching our knowledge of the universe's diversity. Jupiter, as the largest planet in our solar system, serves as both a historical landmark in the study of astronomy and a beacon for future exploration. These discoveries are not only critical for comprehending our own solar system, but also to enhance our knowledge of planetary systems throughout the galaxy. And as we continue to uncover the secrets of Jupiter, we move closer to answering some of the most profound questions about the nature of life, the universe, and our place within it. If you enjoyed this video, please watch future videos and let us know in the comments what future topics you are interested in. And never forget to stay curious.